Okay, so a polyhedron is a three-dimensional figure. We did it, guys. We finally made it to 3 dimensions. We are off a flat sheet of paper, and we're talking about a real-world three-dimensional shape. You and I live in 3 dimensions. Do you know most animals do not see 3 dimensions?
Really?
I don't think so. I just made that up. But I heard on the interweb that maybe that I do not see 3 dimensions. Oh, is it black and white? Sorry, black and color. Okay.
How does that feel like, But how would people know that?
I don't know. Anyway, so we finally made it to 3 dimensions. So on the count of 3, we're going to say polyhedron together because it's a funny word and it's important for us to be able to communicate effectively together. And if we don't practice saying it, then when we say it, it's going to sound funny. So on the count of 3, let's say polyhedron together. 1, 2, 3, polyhedron. All right, so a polyhedron has 3 components. You guys are going to mark these components on your diagram. So you have the word and you have the figure. All you need to do is draw the line. So an edge is where 2 faces meet. It creates a line. So you see how the edge of our polyhedron makes a line. Can we head, shoulders, knees, and toes to make sure we're focusing on the right area? Oh yeah, you got the baby top. All right, so here's what I think of to help me remember face. There is only one part of a polyhedron where I can draw a face. So the one with the flat surface gets the face. It's called a face. I cannot draw a face on an edge. I cannot draw a face on a corner. So it's the face that gets to be called a face because that's where I can draw the face. Okay, so the face is the 2-dimensional surface that creates the side. A vertex is where 3 or more edges come together. I also call this a corner. I call it a corner. So I will call it a vertex first, and if you have a completely blank stare on your face, I will then call it a corner, and then most students go, right, a vertex. Okay, so the requirements to be a polyhedron is that your faces have to be polygons. Polygons are figures that have 3 or more lines that are connected and meet together. So we need 3 or more lines on each of the faces to create a polygon. If I have those, then I have a polyhedron. So we're going to look at A. A is a triangular prism. It's called a triangular prism because the top and the bottom are triangles, and it's connected by a set of rectangles around the sides. Is this triangular prism a polyhedron? Your answer, you have a 50-50 shot. It is because all the sides, the 3 rectangles around the side are polygons, and the triangle on the top and the triangle on the bottom are also polygons. So all the sides are polygons, gets to be a polyhedron. B is a cylinder. Do all the sides of the cylinder, are they polygons? No, so this is big fat no. For this, a sphere. How many sides does a sphere have? No, it doesn't have any. So this is definitely a no, because we don't have any faces. Oh, poor sphere. It has no face. And then D is a square pyramid? And is D a polyhedron? Yeah, because we've got triangles on 4 of the sides and a square or a rectangle on the bottom. All those are polygons. So yes, this gets to be a polyhedron. How is that for identifying? Easy? Better than trying to find the area of a hexagon. All right, so this one is supposed to have, wording, and the wording kind of got lost. I blame the internet. So let me help you out. By pulling up the filled-in notes. Okay. Bigger? Yes. All right, so if you are, so let's come back to our notes real quick. So a regular polyhedron versus a convex polyhedron. A regular polyhedron is a polyhedron with faces that are congruent and identical vertices. So congruent faces, so let's go ahead and circle the 2 things. So when we look at this later and we're identifying, we can go, does it have congruent faces? Are the vertices identical? So, and then a convex polyhedron is a polyhedron if its surface, all the faces, edges, and vertices do not intersect itself, and the line segment joining any 2 points of the polyhedron is contained in the interior or surface. That's a lot of writing. We're going to pause. Go ahead and pause the video and write that down. So when we look at our figure on the right, it's kind of an L-shaped little polyhedron. He is neither regular, so all of his sides and vertices aren't the same. So he's not regular. And I have this little cave that if I wanted to get away from the wind and shelter at night, I can come sit in this cave. Anyway, I would build a fire too, so I can stay warm in my cave. If it has a cave where you can shelter, it is not convex, and if all the sides aren't the same, then it's definitely not regular. So this is neither not complex. It's convex. Oh, silly. So it's not regular or convex. How fun is that? Okay. All right, so if you guys need more time to write polyhedron, let me get, the polyhedron is said to be convex if its surface does not intersect itself, and the line segment joining any 2 points of the polyhedron is inside. So point to point stays inside. There's no little caves that you go outside then back inside in the interior of the surface. You guys on cross section now? So did anybody, I think it was touring either a year or 2 ago, it was the anatomy tour. So there was a cadaver that got sliced thinly, and then so you can see the different, and then put on display, put into panes of glass, and so you could see the interior of the human body. It's pretty cool. Each slice of the person was, you guys didn't see that? Oh, well, you missed out because it was touring. His human body was great. and it tours around, so next time it comes around, we'll have to go. Set up a field trip. So that thin slice is called a cross-section. If you take a thin slice of a human body, it's going to be a two-dimensional human shape. Sometimes, depending upon how we slice the cross-sections of our shapes, we get different two-dimensional shapes. So if we look at slicing a cube and the plane represents our little knife. So we're taking that plane and we're slicing our three-dimensional figure. The two-dimensional figure that happens in A is this guy right here. And that is a square. I will also allow rectangle if you want. Because we really technically have no information that this is a cube. I'm just calling it cube because of the way it looks. So if you want to argue for square, I'd let you argue for square. All right, so if we take our knife and we lop off this corner, because sometimes our sword doesn't hit like square on to the shape, we get a nice little triangle. Then if we take a sphere, we throw it up in the air, and we take our samurai knife, kind of like that with that the Connect game where you chop with the little fruit. We're going to throw our little sphere up in the air and take our samurai sword and slice it in half. We get that shape there, which is called a circle. Samurai sword, circle. All right, so the first three of these we're going to do together, and then because octahedron, dodecahedron, and icosahedron, they have tons of faces, and it's really hard to count them on here. We're just going to fill those in together. Okay, so a regular tetrahedron has this kind of shape here. It is connected, so it's regular. So all those triangle faces have the same measure. All those triangles are congruent. So there are 1, 2, 3, and then the bottom, which is 4 triangles. So the number of faces is 4. And then the vertices are the corners, so we can count the corners. 1, 2, 3, 4 corners. And then edges, so how many lines? We got the one in the back, one on the front, one that's on the front diagonal, and then one that's on the right-hand side. So I get 4 edges. Now hold on. 1, 2, 3, 4, 5, 6. Sorry, there's 6. I have to draw them. You can tell I'm a kinesthetic learner. I have to draw all the edges on there. Catch them with my pencil and count them. All right, so for a cube, we've got, so think about this. How many numbers are on a die? One die, 6. So that means our cube has 6 faces. How many vertices or corners? There's my kinesthetic learning for you. 1, 2, 3, 4, 5, 6, 7, 8 corners. And then my edges I'll do in green. 1, 2, 3, 4 on the bottom, plus the 4 on the top. That's 8, 9, 10, 11, 12. Boom. Regular octahedron. Okay, so now let's go ahead and save ourselves some time. And we're just going to fill this in. So octahedron you look, somewhere there's going to be an 8 rolling around in our process. That is the number of faces it has. An octahedron has 8 faces. It's called octa because of the number of faces. It has 6 vertices, so one on the top, the one on the bottom, and the 4 corners around its middle. And it's got 12 edges. Dodecahedron, kind of like the dodecagon we studied. Dodecahedron has 12 faces. It's kind of that soccer ball, the pentagon shape. All those faces are the same pentagon. So you can take, if you have a regular pentagon, you can attach them all together. Attach 12 of them together to make a nice little dodecagon ball. It has 20 vertices and it has 30 edges. Icosahedron has 20 faces, 12 vertices, and 30 edges. So what we learn from these relationships is, so make sure you guys star and circle, we do Euler's theorem. So go ahead and circle Euler. When I was young in your age, I said Euler, because EU, 2 vowels a walk in, the first does the talking. Euler. Doesn't make any sense. Anyway, it is Euler. Just so we can say the guy's name right. I know he's dead, but whatever. He doesn't care. He's Euler. So let's transfer back to here. Let's do, let's use the formula a couple times. Faces plus vertices equal our edges plus 2. Actually, we'll come back to this. So we'll come back to this on Friday. We'll start out with the rest of these names. Okay, so if we have, find the unknown number. So if we have 5 faces and 9 edges, and we access the equation here, f plus v equals e plus 2, we have 5 faces plus v vertices equals 9 edges plus 2. So it's 5 plus v equals 11. So v has to equal 6. And look at example B. If I have 20 faces, 12 vertices, that's equal to e plus 2. So 20 plus 12 is 32, equals e plus 2. E is equal to 30. Okay, let's look at the soccer ball situation. Soccer ball is made up of 20 regular hexagons and 12 regular pentagons. How many vertices does it have? So if I have 20 hexagons, that is, hexagon is 6, so that's 6 sides, that's 120 edges. And then I have 12 pentagons, so 12 times 5 is 60 edges. I'm going to add those two together to see that my total edges for a soccer ball is 180. And so we look at the picture real quick. So one hexagon, it's the white part here, 1, 2, 3, 4, 5, 6, shares half of its edges with pentagons. So there are 180 divided by 2 unique edges because they have that overlap edges here. So your hexagon had 180, but half of those are sharing. So we divide by 2, and we have 90 unique edges. So we look at how many faces does it have. It has 20 plus 12, which is 32 faces, plus the vertices equals 90 unique edges plus 2. And then we add the 90 and the 2 together, subtract out 32, and there are 60 vertices.